What specific problem does Attamba aim to solve in the context of transformers and long context sequence processing, and how does it address this issue?
Attamba aims to solve the inefficiency of standard attention mechanisms in transformers, particularly the quadratic complexity that arises when processing long context sequences. This inefficiency leads to significant memory overhead and computational costs, especially during autoregressive inference where the key-value cache size grows linearly with sequence length. Attamba addresses this issue by integrating state space models, SSMs, into the attention mechanism, allowing it to compress multiple tokens into single representations, thereby reducing the computational complexity of attention from O(n)² to O(n)² EP, where P is the chunk size. Additionally, Attamba employs cyclic token chunking to mitigate biases from fixed boundaries and preserves leading tokens to maintain full attention on recent inputs, enhancing model quality, while achieving substantial savings in KV cache size and attention computation costs. This innovative approach enables efficient processing of long sequences while retaining essential contextual information.
How does the proposed Attamba algorithm work? Please illustrate its methodology step by step, focusing on the integration of SSMs and the handling of token chunking.
The Attamba algorithm integrates state space models, SSMs, into the attention mechanism to efficiently process long sequences. First, it divides the input sequence into non-overlapping chunks of size, P, where each chunk is processed autoregressively by SSMs to produce compressed key and value representations. Instead of using traditional key-value projection matrices, Attamba replaces them with SSM blocks, allowing multiple tokens to be compressed into a single representation, which reduces the computational complexity of attention from O(n)² to O(n)² EP. During training, the attention mask accounts for both causality and chunk boundaries, ensuring that the model can attend to the compressed states effectively. At test time, only the final compressed representations of each chunk are used, further optimizing memory and computational efficiency while maintaining the ability to attend to recent tokens through leading tokens.
Can you provide a simple example that demonstrates the inner workings of Attamba? Walk through the steps of how a sequence is processed, including the chunking and attention mechanisms involved.
Attamba processes an input sequence by first dividing it into non-overlapping chunks of size, P. For example, if we have a sequence of 8 tokens and P equals 4, the sequence is split into 2 chunks, x(1), containing tokens 1 to 4, and x(2), containing tokens 5 to 8. Each chunk is then processed autoregressively by state space models, SSMs, to produce compressed key and value representations denoted as k(p)-1 and v(p)-1 for the last token of each chunk. During the attention mechanism, the query vector attends to these compressed representations at the chunk boundaries, while also considering the latest partial chunk for self-attention. The attention mask is constructed to account for both causality and chunk boundaries, ensuring that the model only attends to relevant tokens. This approach allows Attamba to significantly reduce computational complexity while maintaining the ability to capture essential contextual information from the input sequence.
What are the theoretical or practical benefits of using Attamba compared to existing methods like traditional transformers and SSMs?
Attamba offers significant theoretical and practical benefits over traditional transformers and state space models, SSMs, by effectively combining their strengths while addressing their limitations. Theoretically, Attamba reduces the computational complexity of attention from O(n)² to O(n)² EP by compressing multiple tokens into single representations using SSMs, which allows for efficient processing of long sequences without sacrificing expressivity. Practically, it achieves over 8 times savings in KV cache size and attention computation costs, while maintaining a minimal increase in perplexity, demonstrating its efficiency in memory usage and computational intensity. Additionally, Attamba's design allows for flexible chunking of tokens, which mitigates biases from fixed boundaries and enhances model performance, particularly in long context tasks. Overall, Attamba's integration of SSMs into the attention mechanism results in a robust architecture that balances efficiency and model quality effectively, outperforming traditional transformers and SSMs in various scenarios.
How was the effectiveness of Attamba validated or tested in the paper? Discuss the datasets, benchmarks, and metrics used in the experiments.
The effectiveness of Attamba is validated through experimental results on the Wikitext-2 test set, where training is conducted on 10% of the DCLM baseline 1.0 dataset, utilizing a batch size of 16 and a sequence length of 1024. The model is trained on approximately 1 billion tokens, and perplexity is the primary metric used to evaluate performance. Comparisons are made against transformer baselines, MNGRU, Hawk, and Mamba models, all within a parameter budget of 60 to 64 million parameters, ensuring a fair evaluation. The experiments highlight that Attamba consistently outperforms these baselines, particularly when matched for KV cache size and attention map dimensions, demonstrating its efficiency and scalability for long context tasks. Additionally, the paper notes that Attamba achieves significant reductions in KV cache size and attention computation costs, while maintaining a minimal increase in perplexity, further validating its effectiveness.
What specific results were achieved with Attamba, and how do these results demonstrate its performance relative to traditional transformers and SSMs?
Attamba achieved significant performance improvements by compressing the sequence length for keys and values, resulting in an approximately 8 times reduction in KV cache size and attention computation costs, particularly during inference. When compared to traditional transformers, Attamba consistently outperformed them when matched for KV cache and attention map size, demonstrating its efficiency especially as sequence lengths increased. For instance, Attamba exhibited only a 2% increase in perplexity when transitioning from a chunk size of 4 to 8, indicating its ability to maintain model quality while enhancing efficiency. In extended training experiments, Attamba outperformed fair transformer baselines and Mamba, showcasing its robustness in handling long context tasks without the need for scaling beyond the trained chunk length. Overall, these results highlight Attamba's effective integration of SSMs into the attention mechanism, allowing for efficient, long sequence processing while preserving contextual information.